Welcome in. You know, whenever we sit down to put together a new deep dive, I always think about you, the listener.
Yeah, it's why we do this.
Exactly. Because if you're tuning into this, you are a learner. You're that person who is constantly driven to stay ahead of the curve, who wants to understand the shifting landscape of tech, but who absolutely does not have the time to get bogged down in endless information overload.
Right. You want the signal, not the noise.
You want the signal. And today we have a massive signal for you. Our mission for this deep dive is to explore a pretty radical new framework for how artificial intelligence uses tools.
It is radical, yeah.
We're going to extract the absolute most critical insights from our sources today to understand a concept that sounds completely counterintuitive at first.
Yeah.
Basically, why giving an AI access to the internet and all the tools that come with it might actually be making it less intelligent over time if we aren't incredibly careful.
It's a really bold premise. And to really grasp why it matters, we first have to look at how quickly the foundational architecture has shifted over the last couple of years.
That is the perfect place to start. And we're pulling from a couple of fantastic sources today to build this picture. First, we spent a lot of time diving into excerpts from Architects of Intelligence, Foundations of Generative AI.
Which is a brilliant compilation.
It really is. It showcases the state-of-the-art foundational papers in the Gen AI space. And reading through it, you just get a sense of the sheer velocity of this field.
You really do. I mean, when you look at the progression mapped out in Architects of Intelligence, you see this evolution from models that were essentially just sophisticated autocomplete engines to what we have today, which are autonomous agents. The foundational papers from just the last few years highlight this massive pivot. We aren't just training models to predict text anymore. We are training them to interact with environments.
Like actually doing things.
Exactly. They're writing code, testing that code, debugging it, browsing the live web, utilizing external software. The focus has been heavily indexed on giving these models hands, so to speak, so they can manipulate the digital world.
And the results have been staggering. I mean, we've seen models in those papers autonomously conducting literature reviews for scientific research or acting as incredibly complex travel planners.
Planners that don't just suggest a flight, but actually interface with the booking API.
Yeah, they buy the ticket.
Yeah.
So the prevailing wisdom has basically been, the more tools we give the AI, the smarter and more capable it becomes. Which brings us to our second and main source for today.
The new paper.
The new paper. It's a brand new early 2026 preprint paper from an absolute powerhouse team of researchers. We're talking minds from the University of Edinburgh, Princeton, UIUC, Northwestern, and CUHK. And it throws a massive wrench into that prevailing wisdom.
It really does. The paper is titled Position. Agents should invoke external tools only when epistemically necessary.
Quite a mouthful.
It is, but it essentially argues that our current obsession with giving AI unlimited access to tools is creating a fundamental flaw in how these systems learn and reason. To understand the shift this paper is proposing, we have to look closely at the current tool use paradigm.
Okay, let's do that.
Right now, in most existing agent frameworks, the AI is optimized purely for task success.
Meaning, as long as it gets the right answer, the system is happy.
That is the core of the issue right there. The training mechanisms reward the final output. If you ask an AI a complex question and it immediately fires off a web search to find the answer rather than thinking it through, the system rewards that behavior because, well, the final answer was correct.
Yeah, it got the job done.
Right. But there is virtually no principled distinction in the training between an interaction that was absolutely necessary to solve the problem and an interaction that was just an unnecessary delegation of thinking. The model treats tool use as a free shortcut.
Okay, let's unpack this because I think I have an analogy that makes this crystal clear.
Go for it.
It's like a student taking a math test, and they're asked to solve 2 plus 2. They immediately reach for a calculator, type it in, and write down 4.
Yeah.
They get the right answer. The teacher gives them a check mark, so the system rewards them.
Wow.
But did they really need the tool? They completely bypass their own internal ability to solve a basic problem just because the tool was sitting right there on the desk.
That calculator analogy perfectly captures the dynamic. The reward system, the teacher in your example, only cares about the 4. It completely ignores the fact that the student outsourced a problem they already had the internal capacity to solve.
Right.
And this brings us to the core position of the 2026 paper. The researchers argue that agents should invoke external tools only when epistemically necessary.
Epistemically necessary. That's a heavy phrase. Let's break that down for the listener.
Sure. In this context, epistemic necessity means that a task cannot be completed reliably via the agent's internal reasoning over its current context.
Okay, so if it has the knowledge, it should use it.
Exactly. If the AI has the latent knowledge baked into its parameters to figure a problem out internally, it must do so. External interaction, like pinging a search engine or querying a database, should be reserved exclusively for when the remaining uncertainty absolutely cannot be resolved without outside help.
So we're talking about drawing a hard line between what the AI actually knows and what it has to go out and find.
Yes, a very clear boundary.
But how do the researchers actually define that line? I mean, in a massive neural network, where does the knowledge end and the search begin?
To define that line, the researchers introduce what they call the theory of agent, or TOE. And TOE does something really interesting. It fundamentally unifies how we think about reasoning and acting.
Unifies them how?
Well, historically, computer science has treated reasoning as the internal brain work and acting as the external physical work. But TOE argues that both reasoning and acting are just alternative tools for acquiring knowledge. They are co-equal mechanisms to reduce uncertainty.
Wait, reasoning is classified as a tool. That's a bit of a paradigm shift.
It is a profound shift. The paper divides tools into two distinct categories. First, you have internal cognitive tools.
Okay.
These manipulate information the AI already possesses. When a model engages in chain-of-thought reasoning, reflects on its previous output, or breaks down a logic puzzle using its own parameters, it is deploying an internal cognitive tool.
And the second category?
Second, you have external physical tools. This is the AI using an API, running a web search, or executing code to acquire brand new information from the environment.
That makes a lot of sense when you frame it that way.
Right.
You're either searching your own brain or you're searching the outside world. Both are just methods to fill a gap in your understanding.
And the boundary between those two spaces is what the researchers call the knowledge boundary.
The knowledge boundary.
Yeah, it's an invisible line separating the internal task set, which are the tasks the AI can reliably solve internally, from the world task set, which encompasses the tasks that absolutely require outside interaction to solve. Knowing where that boundary lies is crucial because every single task requires a fixed amount of what the paper calls epistemic effort.
Epistemic effort. So we're talking about the actual cognitive weight or the informational burden required to solve a given problem.
Correct. Think of it as an invariant requirement. You cannot eliminate this effort. An AI policy cannot magically make a complex reasoning problem require less information. It can only shift where that effort is spent.
So if the problem is difficult, the AI has to decide, do I spend the epistemic effort internally by reasoning through it, or do I spend it externally by gathering more data?
Exactly. What's fascinating here is that external tools don't actually remove the difficulty of a task. They just relocate where the difficulty is resolved.
So if the effort is invariant, what actually happens when the AI uses a web search instead of its own reasoning?
If an AI searches the web for an answer, the epistemic effort wasn't deleted from the universe. It was just outsourced to the search engine's algorithm and the author of the web page. And the reallocation of that effort is where things start to go horribly wrong for modern AI models.
Here's where it gets really interesting, because you would naturally think that having an AI that can perfectly outsource a problem to a search engine is a good thing. Efficiency, right?
You'd think so, yeah.
Right. But the paper points out a massive hidden danger in this exact behavior.
They call it capability stagnation. This is the long-term learning consequence of overdelegation. If an AI agent constantly uses external tools for things, it actually could have figured out internally its internal reasoning capability stagnates.
Because it's not practicing.
Exactly. Because the training system rewards the final correct answer. The AI's internal reasoning pathways are bypassed. It never consolidates that knowledge. Over time, the model's policy learns to associate delegation, not reasoning, with getting a reward.
It's the ultimate use it or lose it scenario. It actually reminds me of how human beings use GPS navigation.
Yeah, that's a great comparison.
Think about it. Before smartphones, if you moved to a new city, you had to build an internal mental map. You had to reason about north and south, remember landmarks, and consolidate that spatial knowledge. It took mental effort.
Right.
Now we just type an address into our phones and blindly follow the blue line. We get to the destination perfectly. We achieve task success. But our internal sense of direction completely stagnates. We end up forgetting how to navigate our own neighborhoods because we outsource the epistemic effort to a satellite.
That GPS phenomenon is a brilliant parallel, and seeing it applied to artificial neural networks is honestly sobering. The AI is effectively following the blue line for every single query, never building its own internal cognitive map.
Wow.
And to analyze the fallout from this, the researchers break down AI behavior into 4 distinct regimes. These regimes are based on how well the agent's metacognition, its self-awareness of what it knows and doesn't know, is calibrated.
Let's walk through those 4 regimes because I think it really helps to visualize this. Let's use this scenario. Imagine I ask an autonomous AI agent to write a complex Python script to analyze a data set. How does an AI in the first regime handle that?
The first regime is high internal, high external. This is pure brute force. The AI doesn't know its own boundaries, so it just does everything.
Everything at once.
Yeah. It writes complex internal code, but it also frantically calls external tools regardless of whether it actually needs them. In your scenario, the AI might write the Python script, but then run 50 unnecessary web searches for basic syntax rules it already knows just to be safe.
So it's highly inefficient.
Highly inefficient. It causes massive latency, and it's like a frantic guesser throwing everything at the wall to see what sticks.
It gets the job done, but it burns a massive amount of compute and time. What about the second regime?
The second is low internal, high external. This is the underthinking and overacting regime. This is your pure GPS analogy. The AI systematically defers to tools while underutilizing its own internal parameters.
So in the Python script scenario,
The AI wouldn't even try to reason through the logic of the code. It would immediately just search Stack Overflow, grab the first piece of vaguely related code it finds, and paste it in.
I see.
It works sometimes, but it introduces heavy dependency on external systems and completely stunts the AI's ability to solve novel problems.
The lazy AI. It just outsources everything and refuses to think. Okay, let's look at regime 3.
Regime 3 is high internal, low external. This is overthinking. The agent relies heavily on internal reasoning and stubbornly refuses to interact with the outside world, even when external information would easily solve the problem.
It drastically overestimates its own knowledge boundary.
Exactly. In our scenario, let's say your dataset requires a brand new Python library the AI hasn't been trained on. Instead of just using a search tool to read the documentation, the AI relies entirely on its internal reasoning, tries to guess how the library works, and ends up hallucinating an entirely fake API that completely breaks the script.
It's like someone who refuses to ask for directions and insists they know the way right up until they confidently drive their car into a lake.
A very dangerous form of overconfidence, yes. Which leaves us with the fourth regime.
Right.
Low internal, low external.
The Goldilocks zone.
The Goldilocks zone. The agent solves tasks using minimal necessary internal deliberation and invokes external tools strictly when epistemically necessary. It knows exactly where its knowledge boundary is.
So it writes the core Python script using its own reasoning, recognizes the exact moment it hits a gap with that new library, pings the web, wants to read the documentation, and then seamlessly goes back to internal reasoning to finish the code.
Perfect calibration.
So what does this all mean? I mean, identifying that Goldilocks zone is great in theory, but how do we actually get the AI to stay there? If current training methods just reward the AI for getting the right answer, how do the researchers propose we fix this fundamental flaw in the architecture?
The paper lays out several major training implications to correct this. The first major shift is moving toward what they call agentic pre-training.
Agentic pre-training.
Currently, foundational models acquire knowledge through next token prediction. They digest vast amounts of text and learn to predict the next word in a sequence. But the researchers argue that if we want agents to understand epistemic effort, we need to introduce next tool prediction at the foundational level.
Next tool prediction. So instead of just predicting a word in a sentence, the model is learning procedural knowledge. It's learning the structure of when it is appropriate to take an action.
Yes. By learning to predict which tool to invoke given a specific context during its earliest training phases, the agent is trained not just to reason, but to actively decide how to reduce uncertainty. Interaction becomes a foundational modeling target, not just an afterthought.
That makes total sense.
But the more profound solution lies in how we handle the reward systems later in training, specifically reinforcement learning, or RL.
Right, because the reward system is what taught the student to use the calculator in the first place.
Exactly, which forces us to rethink the incentive structure entirely. The researchers argue for agentic reinforcement learning, we have to stop rewarding the AI simply for task success. Systems need to actively penalize unnecessary tool use.
Oh, wow.
If the AI uses a web search for a problem it could have solved internally, it should receive a lower reward score than if it reasoned through it independently. This forces the model to develop highly calibrated metacognition. It has to accurately measure its own internal uncertainty before reaching for a search engine.
Wait, let's slow down on the training mechanics for a second. The paper mentions this iterative loop of reinforcement learning, followed by supervised fine-tuning, or SFT, and then more RL. For those familiar with basic RL, how does fine-tuning specifically help the AI learn when to stop using tools?
It is a great question. Think of supervised fine-tuning as showing the AI the exact perfect transcript of how a master would solve the problem. You aren't just giving it a score, you are giving it a high-quality demonstration. So the iterative loop works like this. First, you use RL to penalize the AI for using too many tools. The AI tries again, but maybe it gets confused and stops using tools altogether, falling into that overthinking regime we talked about.
Right, the driving into a lake scenario.
Exactly. So you step in with SFT and show it an explicit demonstration of the Goldilocks zone, exactly when to reason and exactly when to search. Then you go back to RL to let it practice. By looping these methods, the AI's internal model of its own knowledge boundary becomes incredibly sharp.
I love that.
Yeah.
And it totally flips how we should interact with these tools on a daily basis. Think about it from the perspective of you, the listener. You are probably using some kind of AI assistant at work right now to summarize documents, pull data, or draft email.
Yeah, we all are.
And it's so easy to be impressed when you type in a prompt and the AI rapidly fires off 5 web searches in 2 seconds and spits out an answer. But based on this research, you should realize that an AI rapidly firing off web searches might actually be a lazier or fundamentally less capable system than an AI that pauses searches its own internal knowledge base and actually reasons through the data it already has before deciding to click a link.
That is the critical takeaway for anyone deploying these models. Efficiency isn't just about speed, it's about the appropriate allocation of epistemic effort. An aligned agent is one that respects its own knowledge boundary.
Everything we've talked about so far, this theory of the knowledge boundary and epistemic effort, is primarily focused on language models and software tools right now. Writing code, searching the web, using APIs. But where does this go next?
If we connect this to the bigger picture, the implications of the theory of agent are vast, particularly when we move from the digital world into the physical world. The paper explores future directions, starting with vision agents.
Like AI models that process live video feeds or analyze complex images.
Yes. For a vision agent, the framework holds perfectly. Looking at a specific area of an image or a room isn't just passive observation, it is an external tool used to fill a knowledge gap. Visual understanding becomes an actionable epistemic input.
Wow.
The agent's metacognition has to actively guide its visual attention, basically moving its digital eyes to the regions most likely to resolve its uncertainty without wasting compute analyzing the entire scene.
And I imagine this gets even more complex when you give the AI a physical body.
It does. This extends directly to embodied agents like physical robots operating in the real world. In the physical world, the agent's own body becomes a tool.
The body itself is a tool.
Right. A physical action, like a robot moving across a room or picking up a seemingly empty cup to check if there is liquid inside, is what the researchers call an epistemic move. It is a physical action taken specifically to acquire knowledge from the environment. The robot's knowledge boundary is suddenly physically bounded by what it can see, reach, or manipulate.
That is wild to think about. A robot picking up a cup isn't just executing a mechanical movement command, it's running an external tool to gather sensoromotor data. It's reducing its own uncertainty about the weight and texture of the cup.
And this highlights why we need what is called closed-loop learning. The robot takes an action, receives immediate sensory feedback from the environment, and uses that new data to update its internal model in real time. It is a continuous loop of acting to learn and learning to act.
Fascinating.
Finally, the paper touches on how all of this scales up into multi-agent coordination.
Multiple AI agents working together on a single problem, almost like an artificial workforce.
Exactly. Imagine a scenario where an agent is working on a massive project, assesses its own knowledge boundary, and realizes it falls short. The epistemic effort required is simply too high for its internal capacity.
So it's stuck.
But instead of just blindly searching the web or hallucinating an answer, it actively delegates that specific subtask to a peer agent whose knowledge boundary is a better fit for that specific problem.
It's literally building an AI corporate structure. An AI manager realizes it doesn't know how to code the backend. So instead of trying and failing it, hands the task to the AI software engineer agent.
Right.
That agent reasons internally, finishes the code, and hands it back. The distributed boundaries of knowledge form a massive collective intelligence.
But to do that successfully without devolving into chaos, those agents need structured communication protocols and shared metacognitive modules. They need to know exactly when to ask a peer, when to respond, and when to act independently.
This has been an incredibly dense but profoundly eye-opening journey into the architecture of modern AI. To wrap up our deep dive today, the central thesis we pulled from these sources is that an AI's true intelligence isn't just about having access to the internet or the ability to use every software API in the world.
No, definitely not.
True intelligence is about metacognition. It's about the AI having the self-awareness to know when to use those tools and when it is epistemically necessary to rely on its own internal reasoning. Because if it doesn't, its cognitive growth simply stops.
It requires a fundamental shift from viewing tool use as a simple performance optimization trick to recognizing it as a critical decision under uncertainty that permanently shapes the learning trajectory of the intelligence itself.
And as we close out, we wanted to leave you with one final provocative thought to mull over. We've spent this entire time dissecting the paper's warning that an artificial intelligence's internal reasoning will permanently stagnate if it constantly outsources its thinking to external tools.
Yes.
But look around us. We are human beings living in a world where we are increasingly outsourcing our own daily reasoning, our daily planning, and our complex problem solving to these very AI agents.
It's true.
If this theory of agent holds true, what does this imply about the future trajectory of human intelligence? If we constantly over-delegate our epistemic effort to our digital assistants, are we risking our own capability stagnation?
It is a question we are all going to have to answer in the very near future.
Something to think about the next time you ask an AI to summarize an article for you instead of reading it yourself. Thank you so much for joining us on this deep dive. Keep questioning, keep learning, and we will catch you next time.